Good morning, everyone, and welcome back to day number 3 of the workshop on programmable data planes. Today, we will continue with more topics on programmable data planes. And before we start the program, there are a few updates. The first one, the video of day number 1, the recording of day number 1 has been uploaded to our website, and this is also available through the platform, so the Western Academy platform. That's the first one. Second, all the slides up to day number 3 are now online. So these are the slides that we will be using today. So those are the 2 updates. And the plan for today is to cover 3 topics. We will cover runtime controller. So that means how to communicate with the data plane from the control plane. Let's say we are the network administrator and we want to communicate, we want to populate tables manually. So that is what we are calling here runtime controller. So second topic that we will discuss today is checksum calculation. So there are protocols that require checksum calculation. So we will learn today how to do that. And then we will also talk about the deparser. So the deparser is the last stage in the data plane. We have to build back the packet. That means put in place the modify headers and then the payload, and the packet has to get out through the egress interface. So that's what we are going to be doing today. So with this, we will be completing all the elements that we discussed that are part of the data plane. So again, today we are completing all the elements. What is coming tomorrow and Friday are more advanced topics, specifically how to use counters, meters, register. These are more powerful ways to track flow, where to temporarily store information about flows, and that's coming tomorrow and Friday. So that's the plan. So if there is no questions, I hope that you are doing the labs, and if something is not clear in the labs, feel free to bring here and we can discuss them. All right, if there is no question, let's start with our program. We will go through these 3 topics, and then we will have our first lab related to runtime controller, that is populating and managing tables at runtime. We will have a break. We will go over checksum recalculation and packet deparsing hands-on, and then we will do an exercise. If the time permits, we will be doing one exercise, one of the multiple exercises that are available in the library. And that will be all for today. The slide that I will be covering are here, PDF, PPT, both formats. So I will be using the PowerPoint. And again, feel free to interrupt at any time if there is something that you want to discuss more, or one clarification, or any of you, the lab assistant who have quite a bit of experience with P4, if there is something that you find that we have to mention, feel free to interrupt and add any comment that you find necessary. Okay, let's start with the runtime controller. So what is this about? We are placing ourselves in the control plane, or even on top of this. Here we have a network administrator that could manually want to insert a routing entry or entry in the MAC address table, depending on what device we are configuring. So the point is that here we have a human being that interact with the control plane. The control plane provides an interface so that we can push down information, populate these match action tables. So by default, any match action table is empty. And if you remember the previous lab, we were using a script to populate entries in the match action tables that we were using. So today we will do it manually. It's somehow similar. It's actually the same idea that what we do when we add tables in the routing table or MAC address table, as I mentioned before. So the control plane populates the table entries. Table entries are not populated from the data plane, so it has to come from the control plane. We can insert, we can remove, we can update entries in these tables. And here we have an example. We have the control plane. For example, the network admin issue an insert command. We are adding an entry in the IP forwarding table. Second parameter here. And third parameter here, we have the action. Again, any table has 3 columns. The key, we're calling here match, but this is really the key. The action ID, what to do if there is a match, and the action data. This action data is optional, but in this example, the action data is 4, and the key is 192.168.0.1. So that's what we are doing. And this is just an example. There are many commands that are available. So the simple switch CLI tool is used to populate the tables in the lab series. This is program independent CLI. So what that means is it doesn't matter what our program is doing, this tool, simple switch CLI, is available for all the programs. And the clarification here is important because when we use programmable data planes, we also have program-dependent tools, program-dependent APIs. Now, I believe that we are not using in this lab series. Please let me know, Eli and Jose, if that's not the case. But as far as I know, we are not using program-dependent APIs. So we will be using simple switch CLI during all the labs. Another way to see this is this is just the analogous, the equivalent of if you are familiar with Cisco switches and routers. This is the Cisco iOS command line interface. That's the simple switch CLI. And the BMB2, the software switch that we're using in this lab series, include this simple switch CLI, but the same for commercial switches. The Tofino switch also has a command line interface similar to the Cisco iOS CLI. How does it look, a simple switch CLI? Again, it's just a command line interface. There are some commands available. If we want a little bit of help, question mark, provide a lot of all the command available. And there are also more help, for example, auto-completion, similar to Cisco iOS. If we want to look at the tables that are in the data plane, here we have an example, show tables. There are 2 tables, some information about the tables. If we want to add entries in the table, analogous to add entries in a routing table, that's what we usually call static routing, or add entries in the MAC address table.
When I'm looking at the whole scope of the whole neighborhood, it's going downhill for the complex. I'm just being straight.
So that's about the CLI. We will explore a few other commands during the lab. So in lab number 7, we will be playing with the CLI. So we will be manipulating tables. So we will not do any programming in lab number 7, but just interacting with the data plane, the tables, using the CLI. For example, we will navigate using the CLI tool, displaying ports, tables, actions, inserting, updating, deleting table entries. So that's the goal for the first lab that we will have today. Now, the second topic that we will be learning today is checksum. So what is the idea of checksum? There are several protocols that try to check if the packet integrity was respected from sender to receiver. So to check for potential errors on the way from sender to receiver. And that's what this figure is showing. You can think like, for example, the IP protocol has a field that is 16-bit wide, is the checksum. And what the checksum does is a simple arithmetic computation over all the other fields. For example, you can think these little squares are 16-bit fields coming from the header fields, 16 bits coming from the header fields, and it's just an addition. We run across a hash algorithm, and then we have the checksum that is traveling with the packet. At the other end, the receiver will do a similar computation, and it will compare the computation at the receiver and the checksum received and that was computed at the sender. And if there is an error, the packet probably will be discarded. Otherwise, there is integrity in the packet. The packet didn't suffer any error on the way to the receiver. So that's the idea of the checksum. So we will compute checksum in our P4 program. Now, P4.16 doesn't have any built-in construct for checksum. Instead, they are expressed as externs. That means that checksum algorithms are provided by specific libraries. And this is more platform dependent. So for example, BMV2, the V1 model that we're using, the library for V1 model offers certain checksum algorithm. If we're using a hardware switch, Tofino will provide this checksum functionality. Is not provided by the P4.16 built-in construct. As I was saying before, we will do this. We will compute the checksum for IPv4. What that means is, if you notice here that there is a field, 16-bit field header checksum, and we have to do this arithmetic operation over the packet once there is a modification in the packet. And we know that there is a modification in routers. For example, the time to leave is decremented by 1 every time that is received and processed by a router. And therefore, there will be a modification and a header checksum must be recomputed. So that's why this operation is important. Okay, that's the checksum. That's the second item that we will be discussing today, or we will be doing in the labs. The third item that we will be covering is Deparser. And this is at the very end of our pipeline, at the very end, the last stage, the last process that is occurring in the data plane. So what is the deparser? Somehow reverse of parser. So we want to assemble the headers back into a well-formed packet. So that means we have to put together the headers again. And the way to do that is by writing a program that is expressed as a control, as we see here, and has an output parameter that is the packet. And this is the packet is just the bit stream. So that will be constructed, will be built with all the headers that have to be in the packet. So notice that there is an input parameter header. And if you remember, this header is coming all the way back from the parser. And after the parser, it goes through the ingress pipeline, traffic manager, egress pipeline. So during that process, ingress, egress, there might be modifications in the packet header. And then we have to put back before sending through the egress port. Now, how do we build this parser? Again, first, notice that this is just a control. We are familiar already with the control. We have a module applied, and then we have a method over the packet that is called emit. And what emit will do is to serialize the header. In this case, we are starting with layer 2 because that's the first header. And we are just serializing, putting like a bit stream, all the fields of the Ethernet header. Now, notice here that it says that if valid. If this field is not valid, so the operation, the emit will be just, will have no effect. So will be ignored. Having said that, here we have a complete parser, and this is coming, by the way, from a tutorial that was given by Vladimir Gurevich. So the link is here at the bottom. So the emit method serialize header if the header is valid. And what that means is we can put all the potential headers one after another. For example, the layer 2 first, and then in this example, we have MPLS that is considered layer 2.5, layer 3. Notice we have IPv4, IPv6. And remember, a packet cannot be IPv4 and IPv6 at the same time, or a packet cannot be an ARP packet and IPv4 packet. So, but they will not, only one will be valid. For example, let's say IPv4 and IPv6. So either IPv4 is valid or IPv6. The packet is not both at the same time. So therefore, let's say it's IPv4, only this statement will be valid. And for the IPv6 header, the statement has no effect. So that's why we can write in this way. In this example, something that we didn't do yet, but notice that we're also emitting the layer 4 headers. This is not necessary if we don't parse layer 4. So in this example, the programmer was parsing and probably doing some manipulation over layer 4 headers, and therefore it's putting it back. So the parser is totally independent from the deparser is independent from the parser. And the parser, because it's a control, can have conditional statement as any other control block. However, and I think Eli mentioned this the other day, Eli or Jose, the idea is to try to do as simple as possible, making the code as simple as possible, because the platform might not want to compile, might give errors if the code is has complexity. So that's what we will be doing today. Again, runtime control, checksum, and Deparser. Lab number 8 will be about checksums and Deparsers. Hopefully by the end of this lab, you will be able to implement Checksum, implement Deparser, and with that, you can implement the whole data plane, at least simple processing, simple devices that manipulate, that process Ethernet, IP version 4, version 6. And even if you want to go a little bit beyond, I believe after this lab, we have the capability to process layer 4 protocol headers, because the idea is the same. I mean, all the elements are the same. We are covering all the elements of the data plane. All right, is there any questions or any topic that Eli, Jose, the ones, and Ali, you will be doing the lab that we should cover at this point? I think we cover all. I don't see any questions. So then the plan for now is we are a little bit ahead of time. So we just cover what is runtime controller, checksum calculation, and Deparser. We will start right away with lab number 7. Ali, are you ready? Do you want to share your screen?
Yes, I'm ready. Thank you, Doctor. I'll go ahead and share my screen. Okay. So I'm now in NetLab. I already logged in, and I'll go ahead and make a new lab reservation. So click here, schedule a lab for myself. Then go down to the workshop. And in this
Elliot,
session,
just give us a little bit of time so we can do a reservation as well. I will be doing mine here.
okay.
So we're working on lab 7.
Yes. So I'll go ahead and click on lab number 7. And I will find an empty slot to make a reservation. Just make it. Now this is my reservation. Gonna enter it. Might take a few seconds, especially when someone's like multiple people are reserving at the same time. So now I have the reservation ready. I'll go ahead and split the screen into content and the session. You can unlock it here. So take it to the left. And this is the client. Just wait for a few seconds until everyone made the reservation.
You can change the resolution if you want, meanwhile.
The thing is, it's already like the resolution that I want, but it might change. Is that readable?
Yeah, I think
Yeah, that's better.
Much better, yes.
Okay. So hopefully everyone made the reservation. So here on the left side, I'm showing the content of the lab, where again, every lab has the same format, where in section number 1, we provide the introduction about the lab that we're doing. So in this lab, we're talking about P4 runtime, which Dr. Jorge was talking about earlier. And basically, now we're, just briefly to mention that, in this lab, we're gonna be working from the control plane side, which translates in this figure here. So previously we were working on the data plane side, which is the lower level. We were programming in P4. We weren't using the control plane to like using the CLI manually. We were just like using an automated script to do that. Now in this session,
So Ali, just to interrupt you for a second, this is somehow equivalent to legacy devices, right? We
exactly.
interact, we use the command line interface to add static routes, etc. And that's what we're going to be doing today. But assuming that we first program, which we will not do, but there is a program running there that was written by a programmer.
Yeah, exactly. So just like we use in legacy routers, we log into the terminal and we, let's say, add new entries, static routing or whatever routing algorithm you want. Now in this session, we will do something similar, but now in the sense that we will be basically modifying the tables that we have already written in our P4 program. And we will push entries to the tables that we have customized in the P4 program. And this shows like how it's flexible basically to define and modify, add whatever you want in your like whatever table you want, match, action, keys. So the topology of this lab is going to be it's going to comprise 3 hosts, H1, H2, and H3, and S1's gonna play the role like of a router where it's forward based on the IP address. So it's layer 3 switch or router. So the first step of the lab is to open mini-edit. Go ahead and double click on it. And the password is password, which is the same for all the labs. In step number 2, I will load the topology of this lab, which is lab number 7. So in order to do that, you go click on File, Open, you select the lab, and then put the topology. It's already constructed. You don't have to do it. Feel free if you want to modify it or play with it. So now once the topology is loaded, we will run the emulation by clicking the Run button. So, and once these are grayed out again, it means that the emulation now is running. So you can validate your configuration, or you can basically enter into the terminal of, I'll just go ahead and fix the monitor because somehow it's, I apologize for that. Okay. You can go ahead and enter the terminal of any host by holding the right click on it. So here you hold the right click and you choose the terminal. And now, like once you're now in terminal host H1 terminal, you can launch any command, Linux-based command. So for example, if I want to validate the interfaces of host H1, I can write the command if config. And here basically I'm just like verifying that host H1 has 2 interfaces, ETH1 having this IP address and the loopback interface. And you can similarly do that for H2 and H3. Now in step number 3, we will open the Linux terminal so that we launch the Visual Studio Code, compile the P4 program. So just minimizing these and opening a new terminal. And now in this step, I'm basically opening Visual Studio Code. Lab number 7. So here, once this is just welcome page. So here, Visual Studio Code opens the directory of lab number 7. Here you will see all the P4 files. You have the basic.p4, which combines all, which includes all the P4 files, and you have your main file, which includes the parser, ingress, egress, deparser, and so on. So in this lab again, we will not be doing any programming on the data plane, so we will not touch the P4 program. But as you will see in the lab, if you want to navigate around the files of this lab specifically, you will see that it's already implemented, same as yesterday's lab. So like, let's say I want to go to the parser, you will see that the parser is already implemented for you, so you don't have to implement it all over again. So you have the Ethernet, parse IPv4, and so on. Also, if you go to the ingress, you will see the table IPv4 host and longest prefix match table. So you don't have to do anything in the P4 code. So what we will do now is that we will compile the P4 program as it is, not changing anything.
Ali, may I suggest, can you try maybe increase the to 120 or 130 so it's a little bit more clear? Yes.
Okay.
All right.
It's better.
Yes. Yep. Thank you.
Okay, so now I'm having I will compile the P4 program, basic.p4, by writing the command p4c in Visual Studio Code terminal here. And I'll specify basic.p4 because it's the main P4 file that includes all the files. And we'll hit enter. The P4 compiler will compile the P4 code and generate the basic.json file. So once the basic.json file is generated, I can go ahead and push it to the switch using the command push to the switch. And again, this is like a custom command that we did just to move the file from the host itself to the container, which is here.
And as a reminder, the basic.json is the binary, right? The file that includes all the instruction that goes to the data plane.
Exactly. So this is like the format that the data plane understands. We don't need, like, the P4 program is just like from the programmer side, but this is what's going to be pushed into the data plane. And
Now,
this is what's,
yeah, Ali, and just a clarification here is that you can read this because this is just a software switch that we're using for education. I mean, but really this is the binary that goes in a hardware switch, the real switch. This would be a binary. We wouldn't be able to understand as you are having here.
Yeah. So I'll push the JSON to or the binary file to the switch. And the password is password. Now I'll go ahead and log into the P4 switch. So go back to menu edit, hold the right click on switch S1 and open the terminal. Now, once we are inside S1 switch, we can validate that the JSON file is now pushed to the switch by writing the command ls. This shows the available, like, list all the files within this directory, and you will see here basic.json exists. Now, you can also validate the configuration or the interfaces of the switch using the command ifconfig. So as you will see here, the switch has 3 interfaces: S1 ATH0, ATH1, ATH2. and each one is connected to like H1, H2, and H3 respectively. No, sorry, like interface S1 to H0 is connected to H1, A to H1 connected to H2, and so on. So now once you validate that, I'll go ahead and start the switch daemon and attach the interfaces and also enable logging in the P4 switch by writing the command.
Do you have a question?
Yes, thank you. So just the previous display of the S1 either 0, 1, 2, I saw there's like an internet address 10.0.0.0 on the either 0 port and the just no address on the other port. I wonder what's the function of that 10.0.0.0 and why it's on either 0. Is it just the configuration? Can you set it on the other interface and which part set it?
So you're saying you're just to
Yeah.
make sure you're asking why is there like IP address here but we don't set it here?
Yes, and yeah, basically. I mean, I understand the switch basically, you know, it has we use at the higher level, we just set it at the VLAN, one single IP. Here, there's one on this port, but not on the other port. What's the purpose to set it here?
Yeah.
You want to answer, Ali, or?
Go ahead.
Yeah, so that's a great observation, actually. What should happen here is that we shouldn't have an IP address at all. But I think because of mini-edit, it tried to assign like an IP address to one of the interfaces. Yeah, we should look into that up. It's probably just some bug in the mini-edit, so we should remove the IP address. Now, keep in mind that these interfaces will be understood later on as ports for the software switch. So even if you have any IP address, it doesn't gonna do any difference. But yeah, the correct way to do it is to just remove this 10.0.0.0.
Thank you. Okay, just want to make sure it doesn't have any specific functionality.
Oh, thank you for the observation. We will remove that from the labs.
And there is a second observation question, Vinicius. What would happen if you were to push an incompatible binary to a P4 switch like Tofino? I wonder if the compiler provides a strong warranty not to generate an incompatible or not supported binary.
Yeah, you basically can't like you cannot, based on my experience, you cannot like push the like what you will not have the binaries compiled to you. Like let's say that I'm working on Tofino and I have a bug in my P4 program. So P4C will not generate the binary for you in order for you to push them later.
Eli, do you want to add something? I saw you were about to say something as well.
Yeah, basically what Ali said. I mean, if the program is incorrect, it's not gonna generate a binary. But let's say you have another binary file generated from a different compiler, the runtime or the switch daemon, whenever you start the data plane. Because keep in mind, like in the real hardware, is very similar to whatever you do here with BMV2. So here you write simple switch to launch the daemon. There is something called the switch D for switch daemon, and you pass with the binary. So if the binary is not understood, this program will basically tell you that this is an incompatible binary.
Thank you.
Okay. So I'll go back to switch S1, number 2. And I'll start the daemon. Simple switch. And -I stands for interface. So port 0 is gonna be associated with interface S1 ETH0, another interface which associate port 1 to interface S1 ETH1, and then the third interface which associates port 2 to S1 ETH2. And I will enable logging. Slash VM log.itc, and I will push to it the basic.json, run it in the background, just to make sure that I've written everything correct. So I'm attaching 3 interfaces, enabling logging, and I'll hit enter. So now here you will see that the 3 interfaces are added. I will enter. And next, I will start the switch S1 CLI by typing the command simple switch CLI. So now I'm inside the simple switch CLI, where I can basically run the available commands provided by the P4 runtime. So first, here you're in the runtime CMD. Let's say you wanna know what are the available commands that you can use. In order to do that, step number 3 shows you that you can write the question mark and hit enter. So here, basically, you will see all the commands that you can use in the P4 runtime that makes available to you. So, for example, you can see all the actions, show the ports, tables, and so on. These are all the commands that are available to you. And these are from the control plane side. So let's say we have the command table dump, and we want to see how do we use it. So table dump, basically, it as the name shows, it dumps the table itself. So I will write help table dump. So here it displays a description of what this command table dump does. It displays entries in a match action table, and also it shows you how to use this command. So once you write table dump, it expects you to provide the table name that you want to basically display the entries of, or you want to dump. And similarly, you can use this command help with any other P4 runtime command that's shown here. For example, clear, delete, entry, and so on. No, the next section, what we'll do is we'll display the ports. So show, just to validate that, the switch ports. And now, as we see here, because when we enabled the daemon, or when we started the daemon, we attached 3 interfaces, which is, if I go back up here, just to show you, once I started the daemon, I attached 3 interfaces. Port 0 is attached to S1 ETH0, and the status is up. Sometimes, like if there's a port that it's not working, you might need to check the status just to troubleshoot it, see maybe packets are not, it's in a down state, so packets are not being received. So this, you can basically troubleshoot it from here. And similarly for ports 1 and 2, they're all up and running. Let's go back down where we were. Now the next step is that we're just basically playing with the commands that are available and exploring them. So let's try the command show tables to see what are the available tables in our P4 program specifically. I'll just increase this a little bit. Okay, so this command show tables will basically display the tables in our P4 program. So the first table here is called IPv4 host, and my ingress is that because this table IPv4 is inside the ingress control block. And if you want to validate that, you can go to your ingress, and this is the table name, and it's inside the my ingress control. So my ingress.ipv4 host. So sometimes you might have tables in your egress. So this will be changed to, like, if your egress is called my egress, so it will be changed according to your egress control block name. Now, IPv4 host table, it doesn't have any implementation. So this is a little bit advanced, or basically you can specify an implementation of your table, where, like, just briefly, you have the option in P4 to not specifically specify the action, but rather like to specify a pointer to another table where it has the action. It's useful in some optimization, or like when you have a lot of entries that they all point to the same action. So you might use that, but this is a little bit advanced. In our table, it's simple. So it only has the key and the action. Now, next, you will have the key. So in the IPv4 host, we are matching against the IPv4 destination address. And the match is exact. We're using exact match. And the number of bits of the IPv4 is 32. And again, you can validate that from here. You have the destination address, IPv4, exact match, and 32 bits. Now, similarly, you have another table also in your ingress control. It's called IPv4 for the longest prefix match. And the key is the same on the IPv4, but it has the longest prefix match and rather than exact. And it's also 32 bits because that's the size of the key you're matching on. Now we've displayed the keys of the tables. What if we want to display the actions within this? What are the available actions? So let's create and show actions. It would display all the actions. So in our case, we only have two actions. The first one, both are in your ingress. The first one is drop. It doesn't have any parameters. And the second one is my forward. It takes two parameters. These are the action parameters. The first one is the destination address, the MAC destination address, which is 48 bits. And the second one is the port number. So I'll go back here and just show it to you how it's being translated from P4. So drop here doesn't take any action parameter, it's empty. And the forward takes two parameters, the destination address and the port. So this is basically a translation from P4 to the runtime command. Now, you can display some of the switch basic information using the commands switch _info. So this is the device ID, it's 0. The thrift port, which is it uses to this is the port that basically communicates with the control plane. There's like for the nano logging as well. So these are like simple information. Now, there's also a command where you can basically see how long has the switch been turned on, and it's up and running. So you can use the command get time lapse. And you will see here this this number is basically in microseconds. It represents how long has a switch been on? So let's say if I stop the emulation and run it again, it will start from 0 and increments it in microseconds. Just make sure everything is clear and no one has any question before I proceed.
Yes, I do have a question.
Go ahead.
Okay, so before this command, simple switch CLI command, we mapped the ports to the switch port, and I made a typo on the third one. So when we map 2 at S1 Ethernet 2, I made a typo. Then I run the CLI command, and when I show ports, I only saw 2 ports. So the 0 and the 1. So I went out, queued the process, remapped the ports. Then I rerun this CLI command. I still just see the port 0 and the 1. The second one is still not there, but I already mapped it.
So one thing, you said you tried to kill it and do it again. And
yes, I cleared the simple switch process. Then I remap.
okay.
So there.
Can you try one thing where you stop the emulation and then run it again, and then push the P4 program to the switch?
Okay, I'll do that. So
yeah, maybe that will work. Maybe it's something wasn't working like in the interfaces of the switch.
sure, I'll try. Thank you.
So, and Adi, you can also, you are an instructor here. You can access the pod of Shuju.
Oh, you want to do it right now just to see?
It's if she's not able to fix it, yeah.
Okay, I'll just wait until you.
Oh, Istvan also has an observation. CMD not found for simple switch CLI. So Istvan, are you okay? We access, or Ali access your pod. So Ali, you might, I think that would be the easiest way to address if checking the command.
Okay,
Yeah.
I'll go ahead and do it right now.
Yeah, you can go over Istvan pod.
Okay, so you're trying to map the ports, right? I'll just go ahead. Can I have control over your port, please?
I think it's just CLI is written all small caps. It should be capital. Can you try that, Istvan?
Yes, let me try that.
Okay.
Too many screens open. Okay, so let's do cap. Let's see. CLI. Let's map just one port. See if that will take it.
Wait, if you're trying to, are you trying to map the ports or are you trying to log into the CLI?
I try to map the port, but if I type without the CLI, that will give me that the command is not good. I'm missing the JSON file. So take a look. Just simply without logging and without typing anything, it's giving me that error that it is input for JSON file.
Okay,
So,
can I try it?
yes. Or I can give you.
Yeah, please.
Okay.
So simple switch -I 0 S1 0.
So it was parameters, Adi, what you are showing here.
Yeah. Basically just attaching them. Nanolog. And just enable logging. I sometimes because like sometimes when I'm writing this command, I enable logging and I forget like to include the JSON. So this might be an issue.
It's
So now,
it's a very long command.
yeah. So
Okay, thank you. It looked like it was working like magic for you.
I can also try the simple switch CLI for you just to make sure that it's working. Okay, so just if something goes wrong, just go ahead and you can try the command again. Maybe you did something like you mistakenly.
Okay, I will check it out what went wrong last time. Well, maybe I mistyped something. That as always happens. Okay, but I will check it out. Thank you.
Yeah, no problem. You can try the commands here, like show ports, just to validate that the ports are up and running as well.
Okay.
Show underscore ports. And also one thing, yeah, you see them now. So you can also use the tab to autocomplete some of the commands. This is very helpful.
Same like in Cisco.
That's correct. It's similar to the Cisco iOS.
So I don't know
Thank
if the issue is resolved for Shuju or
should you let us know if you need help, or you were able to
I'm
solve?
working on it. I just
Okay.
deleted the entire, I'm just restarting and see what happens. Thank you.
Okay.
I'll let you know.
Sounds good.
So I'm back in my reservation. And the last thing that I want to do is now in section number 5, we want to populate the match action tables using the switch CLI. So previously in the previous labs, what we were doing is basically we were using a command for like automatically pushing the rules in the into the switch. We weren't explicitly like specifying them using the runtime command line. So now what we'll do is basically we'll see how do you push the entries into the table using the runtime API.
And for those who are familiar with Cisco, I know some of you are, this is like the equivalent of installing a static route, for example. Of course, this is just an example of what can be done. I mean, in this case, a routing table, but with the programmable data plane, we can use the table for any purpose we want, not only routing table.
Yeah, exactly. So again, you can display information of the table using the command table info, and then you specify the table that you want to display the information. So first you want to specify if it's in your ingress or egress. It's in my ingress. Then you specify the name of the table, IPv4 host, and similarly it will show the information about the table, such as the key and what are the actions that are available in this table. So when you want to use this like command before you push entries into the table, so that like you know what is the format that's expected in this table. If you want to also like just display the action, the actions are already displayed here, but you can along with the key. But if you want to just display the actions, you can write table show actions. I'm clicking the tab to autocomplete, and then my ingress tab, IPv4 host. Here we'll see the actions that this table implements, or basically this table is allowed to use. Now, what if you want to see the available entries in this table? So far, we haven't added any entry to the table. So let's go ahead and double check it. You can dump the table by using the command dump, the table dump, and then specify the name of the table that you want to dump. Here you will see the entries. There is no entries in the table at all because we haven't pushed any entries so far. So what if you want to display here? It shows what are the entries displayed, and as you see, it doesn't show any entry. But if we want to also see what are the numbers of entries in this table without showing the actual entries, you can use the table num entries. It's basically the command is self-explanatory, so that's the way it's easier for you to use. And here you'll see 0, which means that there's no entries in this table. You can also try other tables as well, such as the IPv4 LPM. Now I want to add an entry to the table, but let's say I don't know what's the format of it. I will use the command help and specify table add. This table add adds an entry to the table as it shows in the description. And the format or the syntax of it is table add, the command, and then the table name. What is the action that you want to apply? What's the key or the match field? And what are the action parameters? So let's say table name is IPv4, the action is forward, you're matching against the specific IP address, and you specify the MAC address as well as the port. This custom to the table and the actions that you have in your P4 program. So I will go ahead and add an entry, as you will see here, to the IPv4 host. The action will be forward. So this is the action name. This is the second parameter. And then I'll specify the match field here is the IP address, or basically the key, because the table has the key, the IP address. And then after that, you specify this like arrow, or where you specify the action parameters. So in our case, the action parameters are the MAC destination, which will like use for routing, as well as the port number, which is in our case, if it matches against the 30.0, I will forward it to host H3 attached to port 2. So I'll go ahead and write the command table add, the name of the table, tab, just to auto-complete it, host, and then I want to forward it. Other option is to drop it. And then where's the key? Okay, I'm now matching against 30.0.0.1. Any packet that has this destination IP address will match this table entry. And then arrow, now you specify the action parameters of this action, which is first the MAC address, 2, 3, 4, 5, and then which port you want to forward it to. And of course, this information, like this assumes that you're the administrator of your network, you know what the hosts are connected to, you know the MAC address, or in this scenario, and what are the IP of the host and so on. So once I execute this command, it will show you that an entry is added to this table. This is the key. So the key here is basically represented in hexadecimal, but it's basically the same as 30.0.0.1. Show ports. Okay, yeah, you're welcome. Show. It shows the ports are now available. Okay, so this match key is basically here in hexadecimal. The action is forward, and the run data is the same as we specified here. The MAC address and the port. And here it also shows you on which handle or like where's the handle that this entry was added to, because this is the first entry, so it has a handle 0. The second one will be 1 and so on. Now we will go ahead and just verify that this entry has been added by dumping the table. So table, let me clear the screen, table dump, and where's the table name? My ingress.ipv4 host. And now, as you'll see here, a new entry has been added. This is the handle of the entry. This is the first entry, so it's the handle is 0. There's the IP address represented in hexadecimal, and there's the action parameters. Now you can also see how many entries has been added, like the number of entries. And my ingress host, as you see here, before it was 0 because there was no entry that has been added. Now that we added the entry, it's 1. Another thing, if you want to display the entries of the table, you can specify them by handle or like based on the match key. So for instance, in our case, let's see, I wanna see the entry corresponding to this match key, which should be represented in hexadecimal. So table dump, the same table dump entry from key, and then I specify what's the table, my ingress.ipv4 host, and then what is the key that you want to look. The key is basically in hexadecimal, it's 0x1e 0 0 0 0, sorry, 0 1 2 3 4 5 1 2 3 4 5 1, which is basically translate to 30.0.0.1 as we were showing here. I'll enter. I will show you the handle of the entry. It's in 0. This is the key I'm looking, and this is the action that happens once a packet has this destination, matches the rule. Okay. So another command that's basically also useful here is let's say you want to see what's the entry available at this specific handle. So you can do that by writing table dump entry, and then what's the name of the table, IPv4 host, and then what's the handle. Of course, we only have one entry so far, so it's handle 0, and same information will be displayed. Now, another also a very useful command is, let's say you want to modify the existing entry. So like rather than, let's say, having the MAC address 03, you want it to be 05, and you want to change the port. To do that, you can modify a table entry by using the command table modify, and then what's the name of the table? So my ingress IPv4 host, and then once you're modifying the entry, right? So what's the action that you want to use? You have the option to modify. It's my ingress forward. And which entry you want to modify? I want to modify entry number 0. That's the handle of the entry. And what's the modification that you want to do? Is that I want to change the MAC address to 2, 3, 4, 5. And then I want to change the port to 5, even though the port 5 doesn't exist, but just like for the sake of experimenting. And here, once you modify the table entry, you will see that the entry has been modified for this specific entry. How do you validate your the modification took place? Again, I will dump the table entry, what the table you want to dump, my ingress IPv4 host, and then the handle of the table, the handle of the entry, excuse me. So you'll have the same key, of course, but the thing is that now it's no longer 03002. It changed based on modification. Just want to make sure that everything is clear and no one has any question.
Sorry, I have so many questions. I think I missed where did you create the myingress.ip_host, or was it already in the system?
Okay, so myingress.ipv4 host, I will show you that. So this is how the runtime command line acts. So let's say this table dump entry from key is the command, right? So you want to dump a table. Basically, in our P4 program, that we didn't modify anything in the P4 program in this session. We were programming the P4, right? And in this session, we provide the P4 program as it is. So you will see here table IPv4 host. It's already implemented. We didn't go over in this session, like we didn't implement it, but we provided in Lab 7 just so that we experiment with the runtime command line. So here in the command line interface, you will see IPv4. It's the table that you define in your P4 program.
Thank you.
And why did you write my ingress? Is that because this table is inside my ingress?
Yes.
Does that answer your question clearly?
Absolutely. Thank you.
Oh, you're very welcome. Oh, yeah, okay. Now in the last section, we are gonna manipulate a match action table, but with a different with a different table. So previously, we were basically manipulating the IPv4 host table, which is in the P4 program defined. Now we will manipulate the IPv4 LPM table, which is also in the P4 program. So we will add an entry to the LPM, similarly as I was doing before. Table add. Now it's my ingress. Now not host, I will use the LPM table. Okay. Now what's the action that I want to use? The action is my ingress forward. Also, the action is defined here, forward, and it's implemented by the table. So forward, and then first you specify the key. So the key is the destination address. I want to use 20.0.0.0/8. This is longest prefix match. And then what do you want to do? You want to change the MAC address to 0, 3, 4, 5, 0, 2, and then you want to forward it to port 1. which is basically attached to host H2. Now we see an entry has been added to IPv4 LPM, and here are the information that these are the action parameters. Also, useful commands would be to delete a specific entry in a table. Let's say you want to delete like handle 0 or like the first entry in the table. So what you would do is table delete my ingress.ipv4 LPM handle 0. Now the entry that I've added in this table is basically will be empty because I deleted it here in this command. Other option, if you want to delete all the entries in the table and not just like one entry, what you can do is you can write table clear and then my ingress IPv4 LPM, which means I'm clearing all the entries in the table. Now, if you want to verify that the table is now cleared, you can go ahead and write table to see the number of entries inside this table, IPv4 LPM. It shows 0. With this, this concludes lab number 7. Just like this is what we did basically is experiment or play with the runtime API. We showed how like we display the ports, how do we display the tables, match the actions, how to modify, clear, delete specific entries. And these are, we also showed what are the different commands that are available, the question mark command. There are a lot of commands for like more advanced topics, such as like stateful processing, registers, and so on, which also we'll cover in some of our future labs and like upcoming days. With this, I'm open to any question. Everything is clear, or anyone has any question?
All right. It seems there's no questions. So thank you, Ali. So at this time, let me share the agenda again. All right, so we're a little bit behind. So we just finished now lab number 7, which we populated match action tables at runtime. Now we're gonna have a 10 minutes break. So now it's 1:18. We're gonna be 1:18 Eastern time. So we're gonna be back at let's say 10 minutes from now, so 28. So we're gonna be back at 10:28 Pacific time. All right, so welcome back, everyone. So we are on day number 3 on the workshop. So we just did lab number 7. Lab number 7 was about how we can manage and populate match action tables at runtime. So we've seen how we can use a tool called Simple Switch CLI, and this Simple Switch CLI will connect to the switch daemon, and then it will be able to basically perform some operations on the table, such as modifying entries, adding entries, removing entries, seeing what are the available tables, actions, and so on. So the next lab in this session is going to be about how we can recompute the checksum and how we can write a deparser in P4. So this is going to be lab number 8 in the series. And then if we have some time at the end, we're going to go over one exercise in which we build a packet reflector. So before we start with lab 8, I'm going to go ahead and go over a few slides just to recap. So what are checksums? Checksums are a way so that a certain receiver can verify the integrity of the packet headers. If there is any error that happened during the transmission of the packet, or if there is any entity that modified the headers, we want to make sure that we know that there was some change. And to do so, we have a checksum field in a certain protocol. For example, in IPv4, we have a field for checksum, and this is going to contain a value based on some algorithm implemented on the sender. So if we want to look at how it works, so we have a sender here, and we have some packet headers. So I'm constructing a packet, let's say an IPv4 packet. So we pass these headers to a checksum algorithm. Depends on the protocol. So for example, IPv4 has its own hashing algorithm. Other protocols might have different hashing algorithms. And the output would be a checksum value. Then the sender will append this checksum value to the headers and will send it to receiver. So once the headers and once the packet is received at the receiver side, the receiver will take again the headers, excluding the checksum, will run the checksum algorithm, and will produce a checksum value. Now, if the one produced by the hash algorithm matches the one received originally in the packet, then the checksum is verified and you accept the packet. All right. Now, in some cases, for some reason, maybe there was an error in the transmission, some bits were flipped, so the headers will be modified, right? And you can see here in this square here that there was some modification. And so what happens is when the receiver receives these headers, it will run the hash algorithm, but at this time, a different checksum will be produced, a different checksum value. And because they are not equal, so the checksum will be incorrect, and therefore, usually the receiver will discard the packet or reject the packet. So why do we care about all of this in the context of P4? So usually we have a P4 switch in the middle, right? And we've seen in the previous labs that P4 switches are capable of modifying the packet headers. So we've seen how we decrement the TTL yesterday, the time to live in the IPv4. And so any change really in those headers is going to be problematic, because basically you will be receiving a different checksum value. And so we want to make sure that whatever change that we do in the P4 is not going to lead to having the receiver reject our packet. Right? So let's assume that we have some original headers received from the sender. The P4 switch modified these headers, so we have a new header here. What's going to happen is we're going to run this checksum algorithm in the programmable switch, and this is what we're going to be doing in the hands-on. So we're going to write this checksum here, and then it's going to produce a new checksum value. This checksum value will be again added to the headers, and then it will be sent to the receiver, where again the same process will be repeated. So we're going to recompute the checksum and check if they are equal. Well, if you do this, then the checksum will be verified and we can accept the packet. If we skip this whole checksum calculation in the programmable switch and we modify the headers in the programmable switch, then the receiver will be computing a different checksum, and this is going to lead to having the packet being dropped. So in this lab, we have this topology again, a single P4 switch and 3 end hosts, H1, H2, and H3. And we're going to be implementing the checksum, right? Because we assume that our P4 switch is modifying the header. And specifically, we're going to be modifying the IPv4 header. So we're going to see the impact of computing the checksum, and we're going to see if we leave the checksum without being recomputed, what's going to happen on the receiver side. Okay. So now I'm going to go to the NetLab platform. All right, and as usual, we're gonna do a new reservation, so new lab reservation, and then schedule lab for myself. And then we are still in the same library, Intro to P4 Programmable Data Planes. And from here, we have to select lab number 8, which combines both checksum recalculation and packet deparsing. So click on lab number 8, and then I will select a pod that is available, allocate some more time, and then submit. And now we have our reservation scheduled. We can proceed by entering to the lab by clicking on this Enter Lab button. Okay, so we wait a few seconds till the pod is initialized. And once we see the client here, it means that we're ready to start doing the hands-on. As usual, we're gonna divide the screen. I will have the content on the left-hand side and the platform on the right-hand side. And as usual, like any other lab that we have, we start first by a table of content, overview of the lab, some objectives. The credentials are still the same. So small password. This is the password that you're going to be using in case you need to enter to a higher privilege mode. And then we have the lab roadmap, which shows all the sections that we're going to be covering in this manual. So at the beginning, we have some background on checksums, basically what I was describing in the slides, why they are important. And then an example of how we can write a checksum update in P4. So I will skip this because we're going to be writing this later on in the manual, and I will describe all the syntax. All right. And then the second part is to see how we can modify our deparser, right? And we're going to see the impact of emitting, for example, the Ethernet without the IPv4. What happens if we do that? So all of this we're going to be showing in this lab manual. All right, so starting from section 2, this is going to be our hands-on part of the lab. So as usual, we have to go to our client, and from there, we're going to be launching mini-edit. But before we do that, let me change the monitor resolution. And I will wait a few seconds, maybe like 10 seconds, and then we can start so that you are all done with the reservation. All right, so we're going to start now with building this topology, and we're going to do that again using mini-edit. So you will see the shortcut on the desktop of mini-edit. We double click on it, and then we input the password, which is password all small caps. This will take us to the mini-edit program. And again, we're not going to be building our topology from scratch, so we're going to load it. It's already saved in the machine. So we're going to go to File, then Open, and we're going to navigate to the directory Lab 8. And then we're going to select the Lab 8 topology file. All right. And as you can see, this is the topology that we were talking about during the presentation. So 1 switch, 3 hosts. And this is the same one that we used in the previous labs as well. So now that we have the topology ready, we can go ahead and start the emulation by clicking on the Run button at the bottom left. All right. And also make sure that these are grayed out to make sure that your topology has started successfully. Now, the first step, we need to launch the terminal of the host H1. So as usual, we will right-click on the host H1, hold the right-click, and then select terminal. And there you're gonna issue commands such as ifconfig to verify the IP address and the MAC and so on and so forth. Okay. All right. So now we're gonna go back to the IDE or the Visual Studio Code just to see the P4 program and start by editing it. Okay, so this is now in section number 3, implementing checksum calculation in P4. So first, we're gonna minimize these windows so that we can see the desktop again. And then we're gonna select the terminal on the desktop. So double click there. And this is gonna be the place where we launch our editor, right? And the editor is launched, which is the Visual Studio Code, is launched through the command code. And then the directory where we want to start working. And this is gonna be in P4_labs and lab 8, since we are doing now lab 8. All right. So at this point now, we opened our Visual Studio Code, and we are inside the working directory lab 8. We can see all the files on the left-hand side. These are the P4 files. All right, and just a few seconds, I will change the screen again. Okay, so now we're gonna inspect the P4 code to see what we have there, so that we know what is the starting point and what is missing. The first step is to inspect the ingress.p4 file. So we have to go on the left-hand side and click on ingress.p4 to open the ingress.p4. And what we can see is there is some implementation in the my ingress that is very similar to what we did before, right? So we have an action forward, we have an action drop, we have an IPv4 LPM table that matches on the destination address using LPM match. And we have an IPv4 exact table, which matches on the destination address, but using exact match. And then we have the apply block. This is where we describe the sequence of table execution. But what we need to notice here is that if we look at the action forward, we did some modification to the TTL, which stands for time to live. This is the field that is found in the IPv4 header. So because we are implementing a very simplified version of a router, we know that every time a packet is received on the router, we need to decrement the time to live, right? So we have to subtract 1. And essentially, this is what we're doing here. But because we are modifying this field in the IPv4 header, it means that if we try to compute the checksum, we're going to be getting an incorrect value of it. Again, why? Because we modified some field in the IPv4. All right. So this is already written for us. We don't have to write anything at this point. So we are just seeing that this IPv4 header field, which is the time to live, is being modified by our P4 switch. All right. Next step, we need to navigate to the checksum file, which is called checksum.p4. Right. And again, you will find it on the left-hand side. So there is checksum.p4. And if you go there, you will see that we have 2 controls. So the first one is called my verify checksum. And the second one is called my compute checksum. And the difference between the two is that my verify checksum is where you write the code to verify the checksum of an incoming packet. So let's say you received a packet from H1 and you want to verify its checksum value. You can write the logic here, right? But the second one, which is called my compute checksum, this is where you're going to be implementing the checksum update. So this is where we're going to reassign a value to the checksum field, let's say in the IPv4, such that it will have the value of the updated checksum of the updated headers, right? And by default, we have them both empty. for now, we're just gonna be looking at the my compute checksum. We're not gonna look at the my verify checksum, but they're really similar. And so what we're gonna do now is, before we write the checksum update in the P4 program, let us see if we keep it empty and we compile and we push the program to the switch and we run a simple packet injection, and let us see what's gonna happen with the packet received on the receiver. So again, we didn't do any changes to the P4 program. All we have to do is now compile it as usual using the P4C and then the program name, which is basic.p4. Hit enter, and then we will make sure that we have an output, which is called basic.json. This is gonna describe our data plane specification. And this is the file that we're gonna be feeding to the daemon to know the data plane specification that we wrote in this P4 program. Okay. And then, as usual, after we compile, we need to push the output of the compiler to our switch. And this is done using the push to switch command. We're going to supply to it the output of the compiler, which is basic.json, and the destination switch. So where are we going to push this file? This is going to be switch 1 or S1. Press on enter, and we're asked to input a password here. So the password here is password all small caps. Okay. Let me wait 5 or 10 seconds and then we can proceed. If there's any question, please let me know. All right. So now what we're gonna do is we're gonna verify this configuration. So we're gonna go again to mini edit, right? So we will maximize mini edit, and then we're gonna enter to the terminal of our P4 switch. As usual, we have to go to the P4 switch, hold the right click, and then click on terminal. This will launch the terminal where we're gonna issue commands in the switch. It's a good idea always to verify that the file was received on the switch, right? So this is through the ls to list the content of the current directory. Now we can see that we have a file called basic.json, which is basically what we pushed from this Visual Studio Code. All right. And then next we need to start our switch. And to do that, first we're gonna inspect the interfaces. So I will issue the command ifconfig, and this is showing us the 3 interfaces, S1ETH0, S1ETH1, and S1ETH2. And this is the same topology, so nothing new here. Each of these interfaces correspond to one of the interfaces here on the switch S1. All right. And next, we're going to start the switch daemon by issuing the simple switch command and specifying the location of the interfaces. Okay, so simple _ switch. Now I'm in this command. And then we specify the list of interfaces. So -i 0 at S1-ETH0. So that's the first interface. Second one is -i 1 at S1-ETH1. And the third is -i 2 at S1-ETH2. Okay. So I'm just starting the switch and specifying the interfaces. And then I will also enable logging. So I will use -- nanolog and use a local socket file. So IPC : // and then tmp bm-log.ipc. And of course, we need to specify now the basic.json to instruct the switch that this is the data plane specification that we're going to be using. And finally, use the AND so that this process is running in background. I'll hit enter, and we can confirm that the interfaces were allocated to the right ports by seeing the output of this command. Okay. And the next step is to populate the tables. And we're not going to do what we did in the previous lab where we go to simple switch CLI, although you can do that and it's the same. Instead, we're just going to be using a script that already contains these table entries, right? And before I do that, I just want to show you that whatever Ali was showing you in the previous lab, all these table modification or table add or any of these, we wrote them in a file called rules.cmd in a directory corresponding to the current lab where you are, right? So if I try to, let me just cat here just to display the content of this file. So lab 8 rules. And what you can see here is that there's nothing special. So exactly how you were writing it in the simple switch CLI, you can put it in a file, a text file, put a batch of these commands. And then all you have to do if you want to execute all of them at one time is you will redirect this file as input to the simple switch CLI. Okay. This is useful if you don't want to, let's say you are creating a new program, you are testing, you have a lot of rules, you don't want to reissue all these rules again. So all you have to do is write them one time in a separate file, right? And then whenever you start your new version of the switch, then all you have to do is just issue this command to populate all the table with the table entries that you have in the file. Okay. So simple switch CLI, then we redirect as input lab 8 and then rules.cmd. Okay, and you can have here any number of rules, so there's no limitation, right? You can keep adding, and then just by executing the script, all of them will be added to your switch. Okay, and so what are these rules about? So nothing special here again. It's the same ones as we used in the previous labs, right? So we have 2 entries for the LPM table and 1 entry for the IPv4 exact, just to show that we can basically now send packets from H1 to H2 or H1 to H3, or basically any combination of these two, of these hosts that are available in our topology. Okay. Now, remember that we compiled our P4 program without changing anything, and our checksum calculation was empty, so we didn't update the checksum. In this step, we're going to see what happens if we receive this packet on the receiver side, which is going to be H3 in this lab, right? And to do that, we're going to go to the terminal of host H3, okay? And then right-click terminal, right? And from there, because this is a regular Linux terminal, we can basically use programs such as Wireshark, which is used for capturing packets at an interface and inspecting the content of the headers and the payload. So we're going to be using that program to see how the packet is being received on the host H3 or on the receiver side. So all we have to do if we want to issue or start Wireshark using and see what's happening on host H3, then we have to start it from the terminal of host H3. You can do the same for the other hosts. So if you want to see how the packets are being received or sent out of host H1, you can run Wireshark at H1. Okay, so now we are inside host H3. I will type in Wireshark and press on enter. And this is going to launch the Wireshark network analyzer. And what you're going to see here is the interfaces that are specific to host H3. And again, we're not seeing the other interfaces because we are using network namespaces in Linux, which basically does this separation of hosts, right? So H3 is now considered as a separate host, and it's not seeing any of the other interfaces in the topology. And we know that host H3 has an interface called H3-ETH0, right? And this is the one that is facing our switch. So we are talking about this interface here. And what we're gonna do is we're gonna click on host H3-ETH0 here, and then click on the start capturing packets button, or you can double click on H3-ETH0. So what happens here is that you have this window that's showing you the packets that are being sent to this interface, right? Either leaving the interface or arriving at the interface. Currently, there is no packets, right? Because we are not sending any packet to this host or out of this host. That's why it is empty. Another thing we can do is we can type in some filter so that we don't want to display all the packets that are being received or sent out of this interface. So let's say we want to filter only TCP. So you can write here TCP. You have other stuff you can experiment with. For example, you want to filter by IP addresses, by source IP or destination, by port numbers, and plenty of other things. So for now, I'm just going to be filtering by TCP. And a key thing to notice here is after you type in TCP, make sure to press enter so that this filter is applied. Okay. So as a recap, what we've done so far, we launched Wireshark on host H3, and we are now waiting for packets to arrive to host H3 and see their contents here in this window. Now, to send a packet, we're going to go to host H1 now, and then issue the send.py command from there to send a packet to host H3. So let's go back to the mini edit, right click on H1 and then terminal. And from there, I will send a packet to host H3. So /send, then 30.0.0.1, which is the IP of host H3, and then some payload that we're gonna use after TCP. And by the way, when we use send, .py, the default behavior here is that we have the Ethernet header. On top of it, we have IP, and then we have TCP. After TCP, we have a raw payload, which has the string that we supplied when we launched the command, which is hello world. But keep in mind that there's TCP headers here. Okay. And now we're going to go back to Wireshark to see if the packet was received. And indeed, you can see that there is a packet here that was received. We can see the source IP is 10.0.0.1, which denotes the IP of host H1. We have the destination 30.0.0.1, which is the IP of host H3. The protocol used is TCP, right? And you have some other information that are related to TCP here on the right-hand side. What we're going to do next is we're going to click on that packet. And if you click on a packet, you will see at the bottom here, you have some information related to the headers inside this packet, right? So you can start by seeing here that you have an Ethernet header. And as we know, we have a destination MAC, source MAC, and the Ether type. Then you have the IPv4, and then you have TCP. So if you go to the IPv4, you see we have here like a this red color, which shows that there's some problem that happened here. And the problem is, if you look down, you will see that it's explicitly telling us that the header checksum is incorrect. So the value that was there is 0x52c4, but the correct one, it should be this value. And why we are getting this error? Again, because we did not recompute the checksum in the P4 program after we decremented the time to live field in the IPv4 header. Okay, so you can see that the packet is received on host H3, right? But if you try to use an application like Ping or any other application that that is in the operating system and that it follows all the standards, you will not be able to see the packet. It's going to be dropped. Why? Because your checksum is incorrect. And now we're going to be solving this problem by updating the checksum in the P4 program. So let's go back to the Visual Studio Code. And there, we're going to be writing this block of code under the mycompute checksum. And this code will be used to basically update the value. So let me describe how to read this code here. So we have a function called update checksum. The first parameter to this function is a Boolean that basically specify if the certain header is valid or not. So for example, we want to update the checksum of IPv4, right? Because this is where we did the update for the field. So in order to perform this update checksum, we need to make sure that the packet that's being received on our switch is an IPv4 packet, right? So if it is an IPv6, we don't want to update the checksum, right? Or maybe there's another update checksum for IPv6, but we don't want to execute this specific function here. And so the first field here will tell the update checksum whether it needs to be executed or not, right? And remember from yesterday, this is valid here is a bit that is set whenever you parse a certain header. So we parse the IPv4 on our switch, right? And therefore this is valid will evaluate to true. The next parameter is a set of fields, and you can see we have these curly braces, right? And these fields are the ones that are located into the IPv4 header, right? So I want to recompute the checksum, and the input for this checksum algorithm is all these values. Now, how did we know this? If you look at the RFC of IPv4, it specifies that the checksum value will be computed by having all these fields, the version, the IHL, diffserv, and so on. And then this is going to be used to update your checksum. At the same time, we want to make sure to write them in order here, right? So we start version, IHL, diffserv, total len, and so on. So if you want to look for other protocols, for example, TCP, TCP might have a different way of calculating the checksum. The correct way is to look at the RFC or the standard, and then there you can see the correct way of implementing this checksum. Okay. So all of these will be our second parameter. Then the third one is, where are we going to store the output of this checksum? So we applied the checksum on all these headers. Where are we going to store it? And the answer here is that we're going to store it inside a field in the IPv4 header called header checksum. This is also part of the standard.
We cannot hear you, Ali, for some reason.
Can you hear me now?
Now we can hear you.
Okay. All right. So what I was saying is that we have all these headers. We computed the checksum. The output is stored now in a field called header checksum under the IPv4 header. And finally, the last parameter is what kind of algorithm do we want to use for this checksum? And this is very important. We have to make sure we use the correct algorithm. Otherwise, you're going to end up with a checksum value that is not matching with whatever the receiver algorithm is using, right? Now, how do we know all of this? If you look at the RFC, you should be able to see the right algorithm, and I have it here on the right-hand side. So for example, this is the IPv4, right? And let's see if you... Right, so we are doing all these values and storing them into the header checksum. And how are we computing this checksum? You can read this here, which says that you need to take the 16-bit one complement, and there's some algorithm here. But anyway, all of this is implemented in the V1 model in an algorithm called csum16, right? And this is what Dr. Khe was talking about at the beginning of the day, the externs provided by the architecture. So this extern here is csum16. This is the hash algorithm that will basically perform whatever is in this standard here. Okay, so make sure if you want to use other protocols and they require a checksum, make sure to use the right algorithm. Okay, let's go back, and then I will type in now the block of code here, which is update_checksum. Open the parentheses, and then the first argument is the validity of the header. So IPv4 dot is valid. The second one is the list of fields. So I will open the curly braces and then type them in. The first one is the IPv4.version, comma, to separate them. And then IPv4.IHL, IPv4 diffserv, then we have the total len, then we have the identification, and then flags, then flag offset, then the TTL, then the protocol field, and then we have the addresses. So first we have the source address, and next we have the destination address. Okay. So once we finish all of these, we have the curly brace. Now, comma, we will use our third parameter, which is where are we going to store the checksum value? This is going to be in header.ipv4.header checksum. And finally, the fourth parameter is the algorithm that we're using. So this is hash algorithm dot csum16.
Just be careful. Header checksum in the previous parameter should be all together.
Oh, all right.
Yep.
Thank you, doctor. Okay. And finally, we need to make sure we have a semicolon, right? So this parentheses here is closing the one for the checksum. This is the first parameter. This is the second, the third here, and the fourth. Okay. And again, this hash algorithm comes from the V1 model, right? And if you look at if you just Google V1 model, you will see the source code and you will see all the available algorithms there. For IPv4, we need this csum16. All right. Then don't forget to save your file. So Control S. And then what we're going to do is we're going to restart the compilation, pushing the file again to the switch, and then restart the daemon. So you can always use here the up arrow to retrieve the previous commands. So we have P4C basic to compile. Okay, we don't have an error. And then we need to push it again to the switch, right? So up arrow, and then we can get back to the push to switch, press on enter, and then we're gonna be entering the password all small caps. All right. So now we're done with the editor here. We compiled, we pushed the file. Next, we're gonna navigate to the window of the switch, which is already there. We have the behavioral model. Let's maximize that. And remember that we have a daemon already running, right? So the first step we need to do is to stop this daemon by killing this process. And in Linux, if you use pkill and you pass to it a certain process name or part of the process name, like we're doing here, this is gonna be stopping the daemon. Okay, you can see here it shows terminated. And then we're gonna restart the switch. Again, if you wanna save some time and don't try the whole command again, use the up arrow. You should be able to see the previous command that we inputted before. So I press on enter. We again reallocate the interfaces, but now we are using the new version of basic.json, the one that has the checksum recomputation. Next, we're gonna repush our rules to the tables. So also use the up arrow, it's already there. And then we press on enter. Again, these are the same rules that we had before, nothing changed. And then we're gonna send again now a new packet to host H3, and we're gonna see the what's going to happen on Wireshark. So let's go to the host H1's terminal. All right. And from there, type the send.py 30.0.0.1 hello world. Press on enter. And next we're gonna go to Wireshark and see what happens there. So I will maximize Wireshark. You can see now we have another packet. This is number 2, packet number 2. And you can see it has the same source IP and destination IP, same protocol. But if you click now on this packet here, you can see that the IPv4 is no longer in red, right? So there's no error now in the headers of the IPv4. And to further confirm, you can use the arrow here to expand and see what's inside the IPv4 headers. And if we scroll down a little bit, we're gonna see that we have the header checksum, which is equal to 0x53c4, and it's correct. So it verified the checksum, it's correct now, right? And we are only seeing this correct because we updated the checksum in the P4 program. If you leave it without any updating, you're gonna have incorrect checksum and the packet will be discarded by your receiver. Okay? So that's it for the checksum. Now the second part of the lab, first, if there's any question, please let me know. Otherwise, we will proceed to the second part, which is looking at the deparser code. Okay, so I think there's no questions. So let's proceed to section 6.3, which is about looking at the deparser and updating the deparser in the code. So we're gonna go back now to the Visual Studio Code by maximizing it here. And then after we see here the code, let's go to the deparser.p4 on the left-hand side. So we click on deparser.p4. And what you can see here is similar to what Dr. Khe was showing in his slides, right? You have some headers you want to emit, you specify the order, and then whenever your packet leaves the switch, this is the sequence of headers that you're going to have. In our case, we have the Ethernet header, so header.ethernet and header.IPv4. We are emitting both. Okay. Now, what we're going to do here is we're going to update this code and remove the emit for the IPv4. So let's select this one and remove it. And if you remove this, what's going to happen is the header of the Ethernet will be emitted, but not the header of the IPv4. So that's the only header that's going to be emitted. And we're going to be verifying that in Wireshark as well. So make sure to save the file after removing the emit for the IPv4. And then let's do again the same steps, compilation, and then pushing to the switch. Again, we're going to be using the up arrows to retrieve the commands before. So p4c basic.p4 to compile. And then next, we're going to push the output to the switch. So up arrows again, and we're going to see the push to switch basically JSON S1 command. Okay. So now we have our newly compiled data plane specification pushed to the file system of our switch. Again, the next step is to now go to the switch. So we're going to maximize the S1 behavioral model terminal, and we're going to be restarting the switch with the new data plane specification. So pkill switch, we stop the previous instance. And then we're going to start it again. We can type it from scratch, or we can just use the up arrow because we already did that. You will find that there. Okay. Now the switch started with a new data plane specification. And then we're going to be pushing the tables again using the script. So I'll use up arrow and then push the rules to our switch. Okay. Now the next step is to again send a packet from host H1 to host H3. So let's go to the terminal of host H1, maximize it. And there, you can also use the up arrow to retrieve the previous command and then issue this command, which sends a packet to host H3. All right. Now let's look at the Wireshark window and see what happens there. We're gonna go to Wireshark and we're gonna clear the TCP filter and press on enter. And once we do that, we're gonna see the third packet there, right? The one that we just received. So if we click on it, this is what happens here. So you will see that we have the Ethernet header there, right? So Ethernet, destination MAC, source MAC, and the Ether type, right? And the problem that happens here is that we didn't emit the IPv4 header, right? So we emitted only the Ethernet. And by default, if you don't emit a certain header, what's gonna happen is it's gonna be the P4 switch will add to the header that you emitted whatever that remained in the packet after you did the parsing. So if you give an example, we received a packet on the P4 switch, you parsed Ethernet and IPv4, but we know that the packet has TCP after IPv4 and has a payload, right? And we've seen this when we sent the packet. So we have Ethernet, we have IP, we have TCP, and we have row. So this packet was sent to the switch, but now the switch emitted only the Ethernet, right? And what happens is, because we parsed in the switch the Ethernet and the IP, but we emitted only the Ethernet, so the Ethernet will be there, and then whatever remained in the packet will be appended to that emitted header. So you will see TCP and the row. So in other words, we are emitting the packet as it is, except the IPv4 header. So we're going to have Ethernet and then TCP and then row. And if you look what happens here in Wireshark, you are seeing here IP or Internet Protocol version 4 or IPv4. And you are seeing this because the way Wireshark works is it will inspect the Ether type field in the Ethernet. And based on that value here, it's going to be showing the next header. So we didn't modify anything there. So from Wireshark's perspective, it's expecting an IPv4 header after Ethernet. However, there's no IPv4, there's TCP, and this is showing here that there is some bogus IPv4 version because it's taking the values of TCP. So in summary, what we need to understand here is the deparser is important. You want to make sure to emit the headers in the right order, and by default, you need to emit the headers. And if you miss one header, it's not going to be emitted. And when we say the headers should be emitted, we mean that only those that were parsed. So remember, we didn't parse TCP in our program. That's why we don't have to explicitly emit here the TCP header. Okay, but we parse IPv4, we didn't emit it here, so the program will know that, okay, we don't want this IPv4 header, we only needed the Ethernet, and that's why it emitted the Ethernet. Okay.
So in few words, Eddie, you have to, if you parse the IP and only up to IP, so the payload that is not manipulated by the data plane include TCP and application layer. Similar, if you, for some reason, do not want to process IP, you only parse Ethernet, the payload will include IP plus TCP plus the application.
Exactly.
And at the end of the day, at the end of the parser, the deparser, you build the headers, Ethernet in this case, and then the data plane will automatically append the payload. So, and the payload is what was not parsed at the very beginning. So
exactly.
that's what we are seeing.
Exactly.
All right.
Yep.
I don't
And
see any question. Yeah, go ahead, Eddie.
no, I was just saying that that's basically it for lab 8. So we covered both the checksum and the deparser. And I have to mention, like, you can always not only emit headers that were parsed, so you can always create your own header, right? Let's say there's a very niche application in P4, which is called the INT, or in-band network telemetry. And the goal is to monitor the switches and see some information about the queue and how many packets are there and other stuff as well. And in this INT, every time the packet traverses a P4 switch, a new header will be added, right? So the switch is adding a new header by itself. And so this is possible in P4, and it gives you an idea how powerful it is. You can have your own program emitting new headers, and maybe before it leaves your network, then you can remove all the headers and then leave the packet as it was before it entered your network. Something similar to what they do in segment routing, for example, which is a source routing technique. If you have a domain that is controlled, you can simply say, well, I want to have our first device, our first P4 switch, specify the path that our packet will take in the network. And then as soon as it leaves our network, we're going to be removing the header out of this packet. So all of this is possible in P4, but if you think about it, with the legacy devices, you want to do all of these header adding and modification. This is something that was not possible.
Yes, and what you are mentioning, INT, is one of the key applications of programmable data plane. So we will talk more about that also tomorrow and on Friday. Well, we're done with this lab. We will have a 10-minute break. We're a little bit behind schedule. And then when we're back, we will discuss an exercise. So exercise building a packet reflector. And we will try to finish, and we will go to as far as we can with that exercise. I think we're done with this first lab library. What is coming is just an exercise. So let's have a break. Right now is 11:21 Pacific time, and we will be back at 11:31 Pacific time. Istvan, I see your question. Can you posted yesterday recording? Yes, we'll be posting, I believe, by the end of today, as soon as possible. That's going to be up in the website. All right, so let's start again our last session for day number 3. Jose, you will be working on this exercise, and we didn't do many actually, this is the first exercise that we're going to be doing, but the lab library that we built, this intro to P4, includes several exercises. And the difference between exercise and the lab is that the exercise just give the objective. For example, in exercise 6 is building a packet reflector and explain what the packet reflector is, but there is no step-by-step direction. So this is something that we would like to give to the students, so to make sure that they understand and they know how to do after they go through the labs. So that's the idea of the exercises. So Jose, please feel free to start the exercise.
All right. Hello, everyone. Well, we reached the last item on our first library. I will go back and schedule a reservation in the P4 workshop. I will go to Intro to P4 Programmable Data Planes and select the last item, which is building a packet reflector. This is, as Dr. Jorge mentioned, a bit different, and we will be not going in a step-by-step basis. Instead, we just have the directions, and we will use the previous manuals that we have here as a reference because we are learning this topic. Sometimes we need to review what we already know in order to make these exercises. So I invite you to schedule a reservation with me, and we will be defining the packet reflector. So I will schedule a reservation here. So another objective of this lab is we are going to be programming all the stages in the data play pipeline from the headers to the deparser. And also we are going to run some control plane commands in order to populate the match action table. So let me enter to the lab. I will go through the lab manual briefly. Let me go here. And we provide a description. We provide the resources that we are going to use. As you can see here, we basically are going to use the Ethernet header, the IPv4 header, and the IPv6 header. Then we explain what we want to do. It's very simple. The idea here is generating a packet from host H1, sending to switches 1, which is a P4 switch. We are going to reflect this packet. We are going to send back the packet to host H1 after performing some modification. Note also that we are going to be populating the match action tables through the simple switch CLI application. So then we have some administrative information, the credentials, you already know, the password is password. And then we can start with the step-by-step procedure. So I will undock this, and as usual, I will put this on the manual on the left-hand side, and I will go to the virtual machine here. Allow me to resize the screen. So if you have any question, please stop me. We are gonna do this together. So let's open mini edit. Password is password. I will go and select the exercise number 6. Here we have a folder called P4 exercise. I will select the number 6. This is the topology, it's the simplest one. And then we are able to run the emulation. Okay. Then what we are gonna do, as usual, we are gonna load the programming environment. I will minimize this, open the Linux terminal and run the following command, which is code for exercises, and I will choose exercise 6. And this will load the programming environment. And then in section 3, we have the deliverables. As you can see here, we don't have a step-by-step guide, but we already know what to do because we already done all these steps that are listed here. Somehow, someone who already went through lab 1 to 8 will know where to find this information and how to do them. So what we are gonna do first is defining the headers for the Ethernet, IPv4, and IPv6 protocols. So we go to headers. You can see that this is an empty template. And let me resize this a little bit. And as Ali was showing yesterday, we will be defining the headers. So we start with the definition. I will start with the type def, where we know that we are going to use the Ethernet header. So I will define the Ethernet type for the MAC address. Then I will do the same for the IPv4. So we have a typo here. I will do the same also for IPv6.
So Jose, I think you might want to put IP address underscore T, right?
Mm-hmm. Yeah, so yeah, thank you. And we have IP6. Okay, and then we are able to, we can go and define the Ethernet header type. And also the ether type, which is big 16. Okay, so then we are gonna define the IPv4 header type. Sorry for that. So
Jose,
this,
maybe it's a good idea to scroll on the left to see the headers. No, the manual as you type the headers on the right hand side. Like if you scroll the manual to the top. No, the manual.
Yeah. I see.
Yeah.
Here. So that's a good idea. I will define the headers here and I will start with the version with 4. Verification. Then we have the offset. Then we are going to define the TTL. Then we are going to define the protocol, the checksum, which is 16 bits. And here we can use our type, our type definition, IP4. And destination address. Okay, now we have our IPv4 header. I think they are correct. We shouldn't forget the semicolons here. Anyways, the compiler will give us an error and usually will indicate where we have that error. That will be something useful to see as well. When we are working on P4, sometimes it's an interactive process, so we have to do it several times. Sorry. So bit 4 version, then define the IHL. No, this case we have the traffic class, sorry. And sorry for that. And then we have the flow label, 20 bits for the flow label. Then we have the payload length. Then we have the next header. Then we have the hop limit. Let's call it like this. And then we can use our IP6 header definition, source address, and also for the destination. All right, we are done with the headers that we are going to use for this exercise. And what we are going to do next is assemble them in the header structure. So I will call the Ethernet type that we'll just define, and I will call it Ethernet. Then I will call the IPv4 type, and I will call it IPv4. And similarly for IPv6, sorry. I have a typo here. Trying to do this fast. So we jump into the ingress. IPv6. Okay, so we are done with part A, and then what we are gonna do is we are gonna implement the parser. Before we jump into the parser.p4 file, I will already define the types that we are gonna use for IPv4 and IPv6. So we know that we can define these values as constants. So what I will do is I will do that exactly. Constant bit 16, and I will call it type IPv4 equal to 0x0800. And similarly for IPv6, type IPv6. In this case, this is equal to 0 and hexadecimal value 86DD. All right. And now we are going to jump into the parser and we are going to implement it. So we go here and we can see that the file is empty. We will define the transitions here and the states. We already have the start state, and the next state will be parse Ethernet. So let me define the state. Parse Ethernet. And the first things that we have to do in this state is extract the fields in the header Ethernet by calling the following function. And this will be in header.ethernet. And then we are going to define the transition to the next state. Remember that we can, over the Ethernet header, we can have IPv4 and IPv6. So I will define the transition for those for those headers. So how do we do that? We call a transition. We select. We look what we have inside the header.ethernet, and we see what's inside the ether type. And here we call our constants type IPv4. We are gonna go to a state that we will define, which will be called parse IPv4, as we did in lab 4, I think. Type IPv6, the same. We are gonna parse IPv6. And we shouldn't forget about the default transition, which is accept. We accept the packet. All right, so I think everything is correct here. The next state that I will define will be parse IPv4, which is simply called parse IPv4. And inside this state, the only thing what we do here is extracting the packet, similarly to the previous state. And we extract the packets that are inside header IPv4. And the next thing is accepting. The other transition will be accept, and so we move to the ingress pipeline. Sorry, I have a typo here. We will do the same for IPv6. We are going to extract IPv6, and then we accept. All right, just to recap here, what we have done in the parser is we have the start state, and then we transition to parse Ethernet. Here we might have two options. We can parse an IPv4 packet or an IPv6 packet. The default action is accept. And then we have the corresponding state for parsing IPv4 and IPv6. I don't know if you have any questions. Please let me know. We are gonna proceed with the other state then. Okay, what I will do next, I will jump into the ingress.p4. You can see that this is an empty state, and in this part we are gonna see what we have in C here to see what we have to do. We are gonna implement two match action tables, reflect IPv4 and reflect IPv6, and their corresponding actions will be forward IPv4 and forward IPv6. We are going to use additional information that is provided by the switch through the standard metadata, which is the ingress port. We will need that because we know we have to know somehow what was the ingress port of that packet, so we can return it through that same port. That information will be provided by this metadata. And also we are gonna decrement we are gonna modify the source IP address, and we are gonna decrement the time to live. And that will be for IPv4 and the hop limit for IPv6. So let's do that. And let's start by defining the action forward IPv4. How do we do that? Very easy. We call the action and forward IPv4. Okay. Inside that action, what we are gonna do is we are gonna, as we mentioned here, we are gonna send back that packet through the same port. We do that instead. You already know that we have the standard metadata egrespec to specify the egress port, and that will be the standard metadata, as same as the ingress port. Okay, then what we have to do is we update the in this case we are going to update the destination address. Let me just go back to the figure, because when a packet arrives to this switch, what we are gonna, it will arrive, this will be the source IP and this will be the destination IP. When we send back, we have to perform an action, and we are gonna modify the source IP address, which in this case will be 15.0.0.1. So we have to instruct how to do that, and that modification will be performed by the match action table called reflect IPv4, the one that we are building now. And this will set the new source IP address. Okay, so let's proceed with that. We are in step C. We know that we have access to this field, destination address, and we are gonna set like a, sorry, here I have a typo. We know that we have to get from somewhere this new destination IPv4 address, and actually we are gonna get that new destination. No, I'm sorry. This will be the source address. Sorry, the source address. We are gonna get that from the control plane. We can call it destination IP4. And if we are receiving this from the control plane, we know that we have to define that in the arguments of this function. So I will receive a new IP address from the control plane. So this is a way that we have to define it. And also what I will do is I will update also the destination address. I have to swap them. So I will do the following. Header IPv4. Okay, and I think we are fine with this function. And the last thing that we shouldn't forget is decrementing the TTL, which is header IPv4 IPv4 TTL. We're going to decrement by 1. Okay, and this is how we define the action forward. Then let's define the table. Or we can also do the same, but for IPv6. Let's do that now.
Jose, before you proceed, I think you're updating the destination address to be equal to the source address after you assign to the source address. So maybe you need to swap these two.
Thank you for the observation, Ali. That is because we are like overwriting the value. So thank you. Okay.
Can I ask a question?
Yeah.
This is Stephanie. So the new source address here equals to the passed down destination IP. in your topology, what would be that destination IP? Is it 15 or 172?
Yes, let me go back through the process. When we send a packet to the switch from host H1, we have this source destination IP and this source IP and this destination IP. When the packet is received, it will look at the source IP, which will be 10.0.0.1, and will substitute that IP address by a new one, which is 15.0.0.1. Okay, and that's the one that will be the packet that will be returned. And also, we are going to swap the source IP by the destination IP. So that's the operation that we described here in this action. So I hope that answers your question.
I think so. I think I may be confused from the destination IP with the new source IP, but it should be 15. Is that right?
Yes,
15.
That's correct.
Okay, thank you.
That's correct. All right, so let's do the same for the IPv6. Let's call an action forward IPv6. And what we are gonna do is we are gonna set the egress port as the same as the ingress. Standard metadata, egress spec. That will be the same as the ingress port. Then we'll have the header IPv6, destination address, and we are gonna substitute that by a new source address. Oh no, we are gonna swap here. I'm sorry. IPv6. And then, similarly as the previous action here, we are going to assign a new IP address coming from the control plane, header, IPv6. Let's call it IPv6. So this will come from the control plane, so we have to specify this in the parameters here of this function. And we are gonna decrement the next hop limit. Okay, so we define the two actions. Let me see if I have a typo here.
I don't see any operation there.
Mm,
The -1. Yeah.
I forgot the -1. I'm sorry for that. So let's see. Yeah, I think we are right here. And the next thing that we have to do is let's start with the table reflect IPv4. We're going to define the table. That's very simple. We already know how to do that.
I will pause for a second. So we are already at 12 p.m. Pacific time. We will continue a little bit more until we finish this exercise for those who want to leave, who have other commitment and might want to leave. The video will be uploaded, including this full exercise, hopefully by the end of the day or by tomorrow morning. So we'll be uploading soon. So for those who might need to leave right now, I hope that we will see you tomorrow. We are again starting new content tomorrow, new library, and the more advanced topics that is we'll be covering stateful elements. That's pretty much for today. Again, we will continue, and also we'll, as every day, we will be in the office hours for any questions, any general discussions you might want to talk. So that will be in an hour from now. For those who cannot be in the office hours, I will see you tomorrow. So Jose, you can continue, and we will try to finish this exercise.
All right, so let's define the table that we will use to reflect the IPv4, the IPv4 packet. Let's call it reflect IPv4. Every table has a key, which in this case we will use the ingress port, standard metadata ingress port, and the match type is exact, the one that we can use. Then we have to define the actions, which in this case we just have one action. Forward IPv4. And also we might want to define the action drop that we didn't define. So let's put the size equal to, and then for the default action, we need to define the action drop. Action that will be equal to drop. Let me just define that action here. We already know how to do that. We can review the previous lab manuals in order to see how to do that. And this will be, we will invoke the function mark to drop. And this is the way how we define the action drop. We don't use any parameter on this function. Then we have to do the same for the reflecting IPv6 IPv6 packets. Let's go table reflect IPv6. The key will be the same, equal to standard metadata ingress port, and the match type will be exact, and the actions will be forward IPv6, and we might want to include also, this is up to us, we might also include a possibility to drop packets, so we can add drop as well here, as well in the previous table, which is forward IPv4. So let me just add the drop action here. And let me finish this table by specifying the size. And the default action, which will be drop. Okay, now we define three actions, which is forward IPv4, forward IPv6, drop, reflect IPv4, and reflect IPv6. What we have to do next, as you already know, as we cover in lab number 6, we have to apply these tables. And for that purpose, we are going to invoke the apply block. In this case, we are going to have two statements, which is if we receive a valid IPv4 header, we are going to apply the table reflect IPv4 dot apply. In that way, we will apply the first table that we defined here, this table. Reflect IPv4. But we are also considering IPv6 packets. So what we are going to do is we're going to add an else statement. And if we receive a valid IPv6 header, we are going to apply the table reflect IPv6 like this. And that is for the ingress. I think we are not missing anything here. I don't know if there's any question. So then what we are gonna do is we are gonna jump to the egress, but there's nothing to do here. We are just gonna leave this empty. We are gonna leave the apply block here since there's nothing to do here. And next, what we have to do is apply the checksum. Apply the checksum. So let me go back to the steps here a little bit. We are done with this step. We define the tables and the actions, and we have to update the checksum then for IPv4. Just note that no checksum is needed for IPv6 for this exercise. So inside the apply block, I will update the checksum as Elise showed in the previous lab. So what I will do is I will call the function update checksum. We'll open parentheses, enter, and I will call the statement if the header is IPv4 header is valid. I will use the following fields to do the checksum, which is header IPv4, the version. Then we use header IPv4, the IHL.
So you might want to
Yes, sir.
show. You might want to show. So where are you getting this? I mean, you should have the diagram of an IP packet, so it's not coming just from our minds.
Oh, yeah, I got you. So let me go back here and I will show the fields that I'm using to compute the checksums in here in the left-hand side. And I will proceed with that. Header IPv4.
So the checksum algorithm, as Elise showed previously, it will take all the fields of the IP header with the exception of the header checksum. So what Jose is doing is listing every single field except the header checksum field. So that's what we are doing at this point.
We're gonna use that field, but we are gonna write on that field later. So let me finish with the headers here. We have the identification. And the IPv4. We have the flags. Then we have IPv4. Fragment offset. Then we have the TTL. And finally, we have the header IPv4 dot destination address. With that, we are done with the checksum. Then all this computation will be stored in the header IPv4, the header checksum, we have it there. And we are going to specify the hash algorithm, which is the CRC16. And let me check. I think with that, we are done with the, with the checksum. And then the last thing that we will do is programming the deparser. Program the deparser by emitting all the packets that we just defined, which will be the Ethernet packet.
So we're emitting the headers. Just remember, we're not emitting the whole packet. You are emitting the headers.
Mhm.
And then the payload will be attached to these headers that you are emitting.
Mhm. Yes, we are emitting the headers that we are using in this lab that we defined, which are the Ethernet, IPv4, and IPv6 headers.
So as we mentioned at the very beginning of today, notice that we're emitting IPv4 and IPv6. So that's okay because a packet is either IPv4 or IPv6. It's not going to be both. And even though we are emitting both, I mean, if this packet is IPv4, the statement that emit IPv6 doesn't have any effect for the packet. So that's why it's still okay what Jose is doing, just emitting every single header, even though some of them will not be executed, will not have any effect.
That's correct. Okay, so with this we can say that we finish programming the whole pipeline, and the last thing that we have to do is assemble all these files as we show in lab number 3. I'm gonna jump into the basic.p4 file, and I will insert all the blocks that we have in the .p4 files below. I will call the v1 switch instance. This will be the main instance, and I will call my parser. We have although we are not using, we have to call my verified checksum. Then we have the ingress. We have the egress. We have the checksum, checksum computation, and finally we have the deparser. All right, and I think with that we are ready to go. Let's see if we have a successful compilation. The compilation was successful, and you can observe here that the basic.json file was generated. And what we are gonna do next is sending this to the switch. We already know how to do that. We are gonna use the function push to switch basic.json, and we specify the target, which is switch S1. The password is password. And now I think we are ready to go to switch S1. We created a P4 program from scratch, and now we have to run that P4 program in switch S1 and verify if it's working as we are expecting. So let's see if the file is there. You can see the basic.json is here. And what we are gonna do, what I'm gonna do is running the switch daemon by calling the simple switch. In this case, no issues with interfaces. We just have one interface, which is port 0 is associated to S1 ETH0. And let's enable the log in case we have some issues. We can debug it and see where's the problem. Let me verify if this is correct. Yeah, it is correct. Let's proceed. It's working. We just have one interface. And what we are gonna do next is adding the entries. We are gonna run the control plane application as explained in lab number 7. I will call the simple switch CLI, and that will allow us to populate the tables with the entries that we want. So here,
So
just to,
where in the lab manual is provided that entry, Jose? So
yes, let's go here.
So we are not just coming, Jose is not just bringing this from his head. That's what I want to show.
Yes, we specify that here, right here. We are gonna populate the reflect IPv4 with the entry. In this case, the key will be the port, because that's how we define our table. In the ingress, we are gonna match on the ingress port, and we are gonna substitute this. We are gonna substitute this by a new source IP. So what I'm gonna do here is I will add an entry to the table reflect IPv4, and this is by calling table add my ingress. We have the table reflect IPv4, and we will call the action, which is in my ingress, forward IPv4. We are gonna match on the ingress port, and with that, let me enlarge this. If we receive a packet that is entering through port 0, we know that we have to reflect that packet. We already performed that by the action, and also substitute the new source IP that we specified in the action forward IPv4, the one that we are invoking here. We need to specify the new destination IPv4, which is 15.0.0.1. Let's see, we successfully added this entry. And in this case, we might wanna add also the entry for the table reflect IPv6. Table add my ingress reflect IPv6, and my ingress forward IPv6, which is the action, and we specify the ingress port and the new source IP. Okay, we can see here that we populated. The key is the ingress port, the action is forward IPv6, and the runtime data is the new source IP, which is this IPv6 address.
No,
okay.
So now how could you describe, I see in reflect IPv4 table, there is a column that it says source IP. and then another column, new source IP.
Mhm.
So how is that reflected in your table that you are implementing on the right-hand side? So I don't see the source IP there. So you are matching against the ingress port.
Mhm.
You're not
Yeah,
matching, and it seems in the table that you are matching again the source IP.
Mhm.
yeah, it should, if you see the table, it has multiple or potentially multiple entries because of the 3 dots. So the match key in your P4 program should be the source IPv4 for the reflect IPv4 and
Yeah.
source IPv4, source IPv6 for the reflect IPv6 rather than the ingress port.
Mhm. That's correct. So we can do that modification if we have some time and try the program. So to make this more clear. So what here we for some reason we were using the ingress port. So what we are suggesting is replacing this by the source IP. Let's do that. So okay, and I will do the same for IPv6. This will change a little bit the program. So we are doing what we have in this table. 6. All right, so we change this before program. We have to recompile it. Let's go basic.p4. We have, I think we have a typo here. You can observe that the compiler, if we have a typo, we can see that it specifies where we have that error, and so we can see here it is in the ingress.p4 file line 43, and it tells you that we have a problem with that specific field. So let's try again.
And make sure to save.
I didn't save it. Thank you. And now it compiles. So I will push to the switch again. And now what we have to do next is I will exit this by typing Ctrl+C. I will kill the simple switch application. And I will run again the new binary, the new P4 program. And in this case, we are gonna add a new entry. This time we are gonna use the source IP as the key, and we are gonna replace that by a new source IP. So let me run the simple switch CLI. I will run the command table add. The table is in my ingress, and you can use tab to auto-complete it. In this case, we are gonna add an entry to reflect IPv4. The action is in my ingress as well. It's called forward IPv4, and we will call. In this case, we are gonna use the source IP, and we are gonna replace that by a new source IP, which is 15.0.0.1. In this case, the key is 10.0.0.1, and the action data will be 15.0.0.1. Let's see, that's what we have here. The match key is the source IP. The action is forward IPv4, and the runtime data is the new source IP in hexadecimal. Similarly, we will do the same for IPv6. I will add this, my ingress reflect IPv6, then my ingress forward PV6, and we know that if a packet comes to the switch, will come with this source IP and this destination IP, and we are gonna swap these IPs and replace it by a new source IP. And what I'm gonna do is we are gonna use as a key, we're gonna use the source IP of the packet that is coming, which is and the new IPv6 address will be the action data. Okay, so I think here we are ready to test the program. Let's see if everything works. What I will do next is, let me go back to the steps here. We already populated the entries into the tables. What we are gonna do next is we are gonna run the nanolog nano message application. And after that, I'm gonna go back to mini edit, open a terminal in host H1. I will run the script to see what we are receiving, because we are gonna use this host as a receiver as well. So we start listening what host H1 is receiving, and then I will use the script send.py and to see if we get the packet reflected. So let's see, send.py 10.0.0. In this case, let me go back here. They're specifying the destination IP address, which is the source IP address is the IP address of host H1. Let's verify that. We know that host H1 has the IPv4 address 10.0.0.1 and the IPv6 address that you can see here. And we are gonna send a packet to the destination IP address that we have here, specify here, send.py and 72.0.10. And we are gonna add a payload, hello world. So let's send that packet. We send that packet. I will go to the other terminal that we opened. Sorry, this one. And we can see that the packet is reflected using the source IP address 15.0.0.1 as the one that we have here, and the destination 10.0.0.1. Let me go back. Let me recap. We send a packet from host H1, open the terminal. This is the packet that we sent. We can observe here that we have the Ethernet header, the IP header, and we have a packet that has source address, the IPv4 address of host H1, which is 10.0.0.1, a destination IP address, which is 172.32.0.10. And after we send this packet to the switch, we perform some modifications using match action tables, and we get back the packet, but with that modification, which is a new source IP address, which is 10.0.0.1, and the destination IP address 10.0.0.1, as we were trying to do. We can try the same for IPv6. So we know that we have that script, send IPv6.py. We specify the destination IPv6 address and a payload.
I think it should be CCCC, right?
Oh yeah, thank you for the clarification. Yeah, I was looking here. Should be here. We have a packet. We have the source IP, which is the IPv6 address of host H1, and the destination, which is CCC10. So okay, let's see what we have there. So we send a packet here, and you can observe we can confirm the IPv6 addresses, and we can also check that the reflected packet has changed the with a new source IP, which is BBB colon 1, and the destination is as we can observe here. Then we finally can observe the logs that were hit. For the first packet, we can see that we parse a Ethernet header, an IPv4 header. Then in the ingress, we executed the table. There was a hit on the table, reflect IPv4, and we executed the action forward IPv4. Then we are done with the ingress. In the egress, we didn't do anything. We in the deparser, we reassembly the packet. We also executed the checksum. We updated the checksum. We can see here. We emitted the Ethernet packet and IPv4 packet, and then we are done with the deparser. Then we send an IPv4 packet that enters through port 0. Oh, sorry, enters through port 0. We executed the parser. The parser, we parse an Ethernet header, an IPv6 header. Then we in the ingress pipeline, we evaluated that the first condition is false because, as you remember, in the apply block, we first evaluate if this is an IPv4 header, or if this is not valid, we check if this is an IPv6 header. Then the second condition was true. Then we executed, there was a hit on the table, by ingress reflect IPv6, and we executed the action forward IPv6. Similarly, we are done with the same process, and you can see we updated in IPv6 we didn't update the checksum. There's nothing to do there, and we can see that we emitted the Ethernet and IPv6 header, and then we are done with the deparser, and the output port is port 0, the same as the ingress port, and we already know how to read the ingress port using the standard metadata. And with that, I think we are done with this exercise. I hope these modifications that what we have done during this exercise were useful for you. And if you have any question, let us know.
Thank you very much. And with this, we will finish. We are over time. Suju has a comment, by the way. It looked like a man in the middle. It's somehow a man in the middle doing some modifications over the packet. Yes, that's exactly right. We're done again for day number 2. We will try to upload the recording as soon as possible. And we're meeting again. For those who want to come to office hours, we will be here in about 23 minutes. For those who cannot come to office hours, we will be meeting again tomorrow at 9 p.m. Pacific time. I will keep this Zoom channel open. It's going to be open, and we will be again starting office hours in 23 minutes. So thank you, everyone, and have a good afternoon. Thank you. And then again, welcome to the office hours, day number 3. We finished all the fundamentals of P4 so far. So what we were doing this morning, Wednesday morning, is completing all the topics in the intro to programmable data planes with P4 library. And we even completed this exercise 6 packet reflector. The packet reflector, in order to do so, we use all the concepts that were previously developed in labs 1 through 8. So it's a good exercise. Perhaps I will have my input here for those who Eli, Jose, build the library. Maybe we can do something, I don't know, what is your opinion, more practical that people is more familiar with. For example, instead of packet reflector, or in addition to packet reflector, maybe a NAT example using the same or similar topology. Maybe let me share here. One host.
We already covered that in exercise 4.
Okay.
And yeah, we might need to clarify it a little bit more, the steps in exercise 6, packet reflector. So we provide more information how to define the tables and those stuff. We just listed the step, and that's up to the learner how to do it. So we might need to add some more clarifications.
Yeah, that's my feedback. It was not that clear what was the exercise about. I understand that we exercise really, we use all the concepts. That's the good thing. All the concepts that were learned from lab 1 to lab 8. But in order for a learner, perhaps to better understand what he or she is doing, it's going to be better to provide a little bit more of input, what the reflector is about, and what the purpose is. I don't know if any of you have an input, similar input, or agree or disagree with what I'm saying.
Yeah, we agree. It needs a little bit more clarification for sure.
Yeah, the other thing is during the lab manual, the packet reflector, there was this table that I saw there. Let's see, and just to be in alignment with everything that the learner is learning. Where is exercise? It might need some slide modifications. Okay, so well, what is the key? What is the action? What is the action data? I mean, for somebody who already saw that more extensively, yeah, the key will be the source IP. I don't know if that is clearly described here, but it would be good just to put the tables in the format. And the other thing is, what is the name of the table? Is really reflect IP. I think was in the ingress pipeline. So this should be my ingress.reflect underscore IPv4.
Yeah.
So it has to be a little bit more clear. Otherwise, is loose, and a learner might have more difficulties to complete this. So there is something to improve here. Okay. Anything else you want to talk about, or lesson learned also for us who develop these libraries?
Yeah, I just wrote like the few comments that I saw that they were in the labs. I think we have to fix those. One which was mentioned by the attendee about the IP address. I don't know why this IP was popping by default, the 10.0.0.0. And then the resolution thing. I don't know why it's always, even after we change it, it goes back to the previous one. And there's also the welcome page sometimes in the Visual Studio Code was displaying. So I think like I have a note on all of these, so we should fix them.
Yes, you were talking about the IP address that was appearing in the switch,
Yeah,
and the switch shouldn't have that.
yeah,
Agree. That was a good point from Shuju, I believe.
yeah.
Okay. Let's go to the program for tomorrow. I don't see any comment, questions, suggestions. So let's just work then on what is gonna be tomorrow. So tomorrow, Thursday, we might have a lecture or a presentation from ESNet. I don't know exactly where, maybe at the end. Maybe at the end. So we can, I will be working on the schedule. For now, we will just keep it like that. One question that I have, I don't think we had information about meters. Lab number 8 is going to be about meters. Probably we will be, we might remove this lab 8.
Yeah.
Because we would like to have some use cases, real use cases. There are some attendees that are working on their PhDs or more advanced level, then would be good for those attendees. Christian, for example, to cover some use cases. But before that, do we have information about meters? I didn't remember having seen that in the slides.
Yeah, I mean, there's like a few slides on meter. I think Jose prepared those. The thing is, I was also talking with Jose today. We might not have enough time to go over 5, 7, and 8 because Lab 5 has 25 pages. Lab 7 has, I think, 30 pages. And if you are saying that they're going to be a presentation, so probably Lab 8, we won't be able to complete it.
Yeah, I'm thinking, let's see. Marian and I, we can go over these 3 concepts: metadata, counters, and meters. And then we start right away with Lab 5 and 7. So, Eli, do you want to go over Lab 5?
Yeah, whatever you want. I mean, I'm fine with
and
any of them.
then, or which one would you prefer, 5 or 7?
Doesn't matter to me. I mean, I'm fine with any.
Which one is here? I believe this is the more complex, even though the ideas are straightforward. But this is more advanced, I would say, Lab 7.
If I remember well, the Lab 5 has also, you know, you have to change the queue size and the rate so that you should be able to have a build up and monitor the queue. But yeah, I think Jose is also familiar with this. So wherever you want, we can change the names or.
Yeah. So why don't you work then in Lab 5?
Okay.
And we will have then Ali and Hussein Lab 7.
Okay.
And we will try to make time for this presentation instead of Lab 8. We will try to allocate 30 minutes from 11:30 to 12 because it's I believe an interesting presentation that ESNet might have. So Eli, let's summarize then for tomorrow. Can you just remove this? No need to this. I will cover that in these 20 minutes.
Okay.
Then Lab 5, and then break, and then lab 7, and then break, and then motivation for stateful elements of onP4 and
Mhm.
applications, motivation and applications for stateful elements in onP4. And that will be Mariam, 11:25 to 12, or 11:20 if we save a little bit of time to 11:50.
Okay. Okay.
So everything is shifted to 5 minutes because this is not needed,
Mhm.
right? And that presentation takes place instead of lab 8.
Mhm. Okay.
All right, so that's the plan for tomorrow. Anything else?
Mm,
The video is posted for the first day. You can go, if you go up, you will see it.
For the second day too?
For the second day, I didn't receive it yet.
Yeah, for the first day it's there. Second day, it should be in the platform already. Perhaps I think you can access through the Western Academy platform. You can
Yeah,
take a
I'm
look there.
not seeing it. Anyways, they might upload them later.
I will send an email asking for that, so it should be there soon. Okay. I don't see any more comments, addition, questions. So let's stop here for today. I will stop the recording.